Okay, what are we doing? Okay, so we're going to do a L'Hopital's example. And we'll do let's do number 28. Number 28 from page 441. Okay, and that is the limit as x goes to infinity, the limit as x goes to infinity of 1 minus 1 over x all to the power of x. Okay. Okay, so as you can see, if we just evaluate the integral as is, or not the integral, the limit, you can see that this is going to 1 to the power of infinity. So that means that we are going to be able to use L'Hopital's rule, but we need to, edit it first, right? We need to adjust this. So I'll write L'Hopital's rule with adjustments, okay? So the first thing that we'll do is, I'm just going to say that, y is equal to 1 minus 1 over x to the power of x. Okay, and the whole purpose of doing this is to sort of work out a way that we can take that x out of the exponent. Okay, so we don't want an exponent of x because that makes it really hard to work with. So we'll take the natural log of both sides. So we'll say that the ln of y is equal to the ln of 1 minus 1 over x. Well, instead of having it to be to the power of x, since I've taken the ln, I'm actually just going to multiply it by x over there. Okay, so when I do that, now I can take the limit. I'm going to take the limit of both sides. So we'll say that the limit as x goes to infinity of the ln of y is equal to the limit as x goes to infinity of the ln of x times 1 minus 1 over x. And when x goes to infinity, we should be able to see that I have, well, let's see what happens. When x goes to infinity, this goes all the way to infinity, and I've got 1 minus 0. So I've got infinity times 1. So that is not going to give us L'Hopital's rule. So let's see if we can, excuse me, adjust this a little bit. Oh, no, sorry. Do you see what I did wrong here? Yeah, the x. I put the x in the wrong place. These should be in opposite place. I was a little confused about what was going on there. Okay, so let me just quickly adjust that. That should be x times the ln of 1 minus 1 over x. And that looks a little bit better because this is going to infinity. And then this is going to, well, we've got 1 minus 0, which is 1, and the ln of 1 is 0. Natural log of 1 is 0. So I've got infinity times 1. So this is infinity times, sorry, not 1, infinity times 0. So if I wanted to, I can think of 0 is kind of like, we sort of think of it as 1 over infinity. So let's turn this into 0 over 0 by making that infinity go on as the denominator. So what I'm trying to say is that, let's say that this is equal to the limit as x goes to infinity, and let's put that as 1 over x as the denominator, and the numerator will be ln of 1 minus 1 over x. Okay, and now we should be able to see that the numerator goes to 0 and the denominator also goes to 0. So now we can use L'Hopital's rule. So L'Hopital's rule now applies. Okay. Are you okay with it up to now? Is this okay? Yeah? Okay. So all we have to do next is take the derivative of the top and bottom. So I'm going to get on the top, well, I'll still keep my limit. It's still the limit as x approaches infinity. Well, the derivative of ln of 1 minus 1 over x is going to be 1 over 1 minus 1 over x multiplied by, well, the derivative of the inside. So the derivative of 1 is 0, so I don't have to include that. The derivative of negative x to the negative 1, that's going to be, what is that, positive x to the negative 2, I believe, right? So d by dx of negative x to the negative 1 is x to the negative 2, right? So I've got x to the negative 2. And on the denominator, when I take the derivative of that, I have, it's going to be basically the same thing except negative. I mean the same thing as this. So I'm going to have, well, negative x to the negative 2, okay? And I think it's clear to see that these will cancel out. Not the negative sign, though, so keep that in mind. So I'm going to have that this is equal to the limit as x approaches infinity of negative 1 over 1 minus 1 over x. And as x approaches infinity, this little guy right here goes to 0. So we can kind of think of this as 0. So I've got negative 1 over 1 minus 0. Or in other words, that would be, negative 1. Are you okay with that? Yeah? Okay. So let's not forget what this was originally equal to. So remember that, let's carry down this original limit. So this is actually so the limit as x approaches infinity of the ln of y, that's equal to negative 1. Okay? So now I'm going to take each side of this equation and set that as the exponent on Euler's constant to get rid of that ln. So I'm going to say that e to the power of the limit as x approaches infinity of the ln of y is equal to e to the negative 1. And since we have that e to the limit of something is equal to the limit of e to the something, in other words, we can just take this limit outside because e to the x is a continuous function. So we'll end up getting that the limit as x approaches infinity of e to the ln of y is equal to e to the negative 1. Or in other words, the limit as x approaches infinity of y is equal to e to the negative 1. And remember what y was. Y was just a placeholder for our original expression. Remember, y is equal to 1 minus 1 over x to the x. So we get exactly what we were looking for. The limit as x approaches infinity of 1 minus 1 over x to the x. That's equal to e to the negative 1.